User-defined data types using struct in C. In this lecture, we will learn about how to use the struct keyword and build our own data types in C. So let's jump into Visual Studio to see that in action. Okay, so here I am on Visual Studio. I'm going to create a new project. Let's click on File, New Project. Make sure you have Win32 and Win32 console application selected. Let's go ahead and call this Struct Demo. Click OK. On this page, click Next. On this one, make sure you have Empty Project selected, then click Finish. Now I'm going to add our main.c file. Right click on Source Files, Add New Item. Let's call it main.c. Okay, so in this lecture, we will learn how to use the struct keyword to build our own data types. Basically, the struct keyword allows you to define your own custom data type so that you can have a new type introduced into the language. So here's an example of how you declare it. We use the struct keyword followed by a tag, which is the name of that structure. Struct my structure, for example. Then you open a curly brace and then you close it here, and then you define your members inside. So how do we use it then after we declare it? Simply by saying struct the name of your structure and then a variable of that type. That's the way to use it. Let's see this in an example which make it more clear. Let's say I want to build a struct called point. Now the name of the structure here, the tag, can be all capital. You can define it however you want. For example, let's do it this way. Semicolon at the end is very important. So now I have defined a new structure called point. So our point structure is going to have inside it two variables, x and y, which are also known as fields of the structure. So this is a new type that I just introduced. Now I can declare my variables of this type and then use them in my program. Let's see this inside the main function. Point pt1. The only thing here you need to notice the difference between C and C++ is that in C++ it allows you to use the point like this, reference it directly. But in C, you still have to say struct point. You have to specify the word struct. Otherwise, you get a compilation error. So I could define multiples. Let's say pt1, pt2, etc. So now we have defined two variables of our new data type. Now we can initialize them by saying pt1.x equals 100, pt1.y, for example, equals 100. Then we can say pt2.x equals 200. pt2.y equals 200 or maybe 300. Another way to initialize is you can also say struct point pt3 equals 150, 130. Let's define a function here that says print point. You give it a point and it will print it out. So let's say printf. So let's say we have a function print point, struct point pt, and now we want to say x equals %d and y equals %d, pt.x, pt.y. So now that I have this function, I could easily say print point pt1. I can also say print out pt123. Let's compile this and run Ctrl F5. Yes. Now as you can see, the first point has x equals 100, y 100. The second point we said x 200 and y 300, and the last one was 150 and 130. So different ways to initialize them, and this is how you pass them to function. In this case, we're passing by value and we're not passing by reference. So what's going to happen is that this variable here is actually a copy of the value that you pass here. Another way to pass it is to just say a pointer. And then in that case, you will not be passing in another value, but instead you're passing by reference. Let's try another example. We could say struct rectangle. Now our rectangle could potentially have a struct point pt1 and the struct point pt2. Let's define a rectangle here. Let's say rectangle rc1. We still have to use the struct keyword in C. So we can say rc1.pt1 equals pt1 and rc1.pt2 equals pt2. This is actually an example of a structure type that is also using another structure type. It's completely fine. So this is how we define and use our own custom data types. You can continue. You can define struct employee. Then you can say, for example, char name of 100. Integer age of that employee, integer employee ID, You can say something like float salary, etc. So we just defined an employee structure that we could potentially use. Let's define a list of employees, something like this. We could say struct employees of 100, for example. Now here we have defined a list of 100 employees. We can go say employee of 0 dot name, and then we can use strcpy into this name, employee 0. So this is pretty much how you define and use structures. It's a very useful data type, and in future lectures we will also touch base on it one more, especially when we introduce the typedef keyword, to see how we can avoid using this struct keyword over and over again. That's it for this lecture. See you in the next lecture. Working with unions in C. In this lecture, we will learn how to define, declare, and use a union in C programming language. So let's get started. Here I am on Visual Studio. Let's create a new project, File, New Project. Let's call this one Union Demo. Click OK. Click Next. On this page, click Empty Project, then click Finish. Let's right-click Source Files, add New Item to add our main.c. Click Add. Similar to structure that we touched base on in a previous lecture, the union can be defined as following. You can say union, give it a tag name, and then curly braces. Then you have your members inside the union. Let's say union, my union. Let's say we have integer a, float b, then char str of 10. The main difference between a union and a structure in C is that in a structure, you're building a custom data type that contains multiple different members. In the case of union, it's a slightly different, where these members are actually sharing the same memory location. So the union in memory will actually be the size of the largest of all its members. So in this case, we have 10 bytes. So the size of this is going to be only 10 bytes. Not like the structure where you have, let's put this side by side so we can understand. Say I have a struct here, my struct. In the case of a structure here, this has 4 bytes, and this has 4 bytes, and this has 10 bytes. These are considered individual fields inside the structure. So when you define struct, my struct, let's say S1, and you define here union, my union, U1. The first main difference is that this structure has different 3 members, each has its own memory space. So the size of this struct is going to be at a minimum 4 plus 4 plus 10, which is 18. There might be some padding in memory. It could take more memory for efficiency, but the minimum is going to be this. However, in the case of the union, it will actually try to merge all of these into one single memory location that is accessed by these individual members. So think of it as different views on the same memory location. In this case, it's going to be only 10 bytes. You can look at it as a stream of characters of 10, or you can look at it as a float, or you can look at it as an integer. Okay, so now the first thing we want to verify is the sizes. Let's do this. Let's say printf size of S1 equals size of S1. It's the same as the size of the structure. Now let's do the same for size of U1 equals size of U1. First thing we want to verify is the sizes to understand this. So Ctrl F5 to compile and run. Yes. Okay, so as you can see, S1 is 20 and U1 is 12. For efficiency purposes, the compiler might add some padding and make this in memory take more space, but at least it's going to be enough space to hold all these individual elements inside it. Whereas as you can see in the case of a union, the size was 12. Actually, let's make it this way, 100. Okay, so if we make it 100 instead of 10, just to make it more clear because of the padding that we saw previously. So now I made it 100. So this one will be 108. And if it's a multiple of 4, it will be good. There may not be any padding. In this case, also, same thing. This will not take up any more space, even if we define integer, let's say integer A1, integer B1, integer C1. This is just to show you that it will not be any extra memory. Ctrl F5 to compile. So as you can see, the structure is 108, the union is 100. Like I said, the union here is only going to allocate enough memory for the larger size, and these become just different views on the same memory location. Whereas in the case of a structure, the memory size is the size of all of its individual members added together. Okay, let's say s1.a equals 100, s1.b equals 200, and then s1.str, let's copy to this some text. This is inside a structure. Okay, so this do the same for u1. Let's say now u1.a equals 100, u1.a1 equals 200, u1.b equals 300, and then u1.str equals, so I think the b here was float. Let's just change the name to reduce confusion. Let's make this f. The string is going to be something similar to this. I'm going to copy it here. Say u1.str, this is inside a union. Then this printf u1.a. Okay, instead of writing a lot of printf statements, one better way to check out the values is set a breakpoint here. I'm going to hit F9 on the keyboard, Ctrl-Shift-B to compile. Okay, I have some warnings in here. I forgot to include string.h because I'm using string copy. I'm going to say include string.h. Then this should get rid of the warnings. Ctrl-Shift-B. Just before we compile, I have added define CRT secure no warnings and included string.h because I'm using str copy here and it's warning me about it. It's being not secure, etc. So Ctrl-Shift-B to make sure it's okay. All right. I'm going to set a breakpoint here by hitting F9 so that I can actually use the debugger to quickly see the difference between the two. So on the keyboard, I'm going to hit F5. It will actually run and then stop at my breakpoint here. So let's look at this with right clicking and then go to quick watch. It's Shift F9. Now I'm looking at my S1. As you can see now here, S1 has A value at 100, B value is 200. The string has, this is inside the structure. Now let's look at U1 at the same time. Here, hit U1, expand it. As you can see now, all the variables inside it have exactly the same value, but translated based on their type. And the value that they have is the same value that was set by the last member, which is the string. So in this case, you're not going to maintain different values. They're all going to be pointing to the same memory location, and they're all going to be pointing to the same value of that memory location, but different views on it, different translations of the same value. Let's say I change here this A1. Let's say I change this to 100. What's going to happen here? As you can see, I changed A1 to 100. Now B1 is 100, C1 is 100, A is 100, F is showing that in its own format. And then string is showing you the ASCII representation of the 100, which is D. If I say here 97, which is the A, then now you can see they're all showing me A. So let's say we change this value, the float value. Let's zoom in. As you can see, a 99 in a float presentation is actually not going to be the same as an integer representation. You see, the integer values get translated differently. Same for the string, but the idea here is that a union is useful if you want to combine and pack all data into one memory location and try to access it with different data types, look at it differently from different points of view. Back to our example here. Okay, so this is the main difference between union and struct. You will find out that this union is not used as much as you use the struct. Struct is used more often. There's rare cases where somebody would need union, but again, I'm sure in low-level system programming, there has been cases where there was a need for union. That's why it was introduced. Other high-level languages like Java, C#, they don't have the equivalent of a union. This is something geared towards low-level more than high-level. But again, C is a hybrid high-level, low-level language. That's it on unions. I hope this is clear enough to understand unions. The best way to do it is to practice it yourself. Please take the time to practice and do it yourself. See you in the next lecture. In this lecture, we will learn how to use auto, static, register, and volatile keywords. We will look at how they are used, when to use them, and when not to use them, etc. So let's get started. Okay, so here I am on Visual Studio. Let's go ahead and create a new project. Click on File, New Project. Make sure you have Win32 and then Win32 console application selected. Let's call this one New Keywords. Click OK and then click Next. On this page, make sure you have empty project selected, then click Finish. Let's add our main.c file by right-clicking on Source Files, Add New Item. Let's call it here main.c, then click Add. Okay, so let's look at these keywords and what they mean. Let's start with auto. Auto is a modifier that defines the storage class of a variable. By default, each local variable is considered to be auto, so you don't really actually need to use it. However, let's take a look at how it's used. For example, let's say we have an integer n equals 100. A modifier means something that can be added to the data type as following. We can say auto int n. Can be specified this way, or you can say integer auto n. Okay, so in this example, as you can see, we just defined a local variable n with a value 100. The auto keyword is completely optional. It just says that this variable gets automatically allocated and deallocated on the stack. All local variables by default, you don't have to allocate memory for them. They just get allocated by the compiler behind the scenes for you. So really the word auto here is just redundant. It doesn't do anything. You don't have to specify it. However, since it's part of the C language, we just want to make sure we understand how it's used. Don't confuse this with the new C++ auto keyword. That's a completely different use of the keyword. Here, it's just a modifier that you can use and specify, saying that this is an integer that is local, and that means it gets automatically allocated, and then once you leave this function, it gets automatically deallocated. So what really auto is saying is that local variables get automatically allocated when we enter this function, and when we leave the function, they get deallocated, removed from memory. You don't have to use it. By default, all local variables are auto. So it's just a keyword that's optional. It's good to know what it means. That's it for this lecture. See you in the next lecture. The next keyword in C here is called register. Register is used to define variables that you can actually store inside CPU register instead of RAM. If you remember from our very first section on Introduction to Computer Programming, etc., we touched based on CPU registers. When you specify the keyword register with a variable, that means you want it to be stored inside a register for faster access, quick access instead of RAM. So the only place you should use this is for things that require quick access, like for example, a counter, a loop variable. The other catch you need to understand is that once you say register, you cannot use the address of operator with that because it will not be in memory, it will be in a register. So let's look at an example here. Let's say we have integer I. So now let's say I have a loop for I equals 0, I is this 100 plus I, and I want to print out this thing. So since we have a loop counter here, we can just simply come here and say register integer I. So we're telling the compiler we would like to put I inside a register. So that's an example of where you would use register. You just tell the compiler, I'd like to use I inside a register instead of RAM for faster access. So now we can no longer do the following. We cannot say memory of I equals %p for pointer, and then we can try and say address of I. This should not be allowed because the compiler may put this inside a register, not memory. And as you can see here in the output, as I compile, it's telling me here error address on register variable. You cannot use it. So you can't do this. One very important thing to notice is that register is only a recommendation or like suggestion from us, the developers, to the compiler. So meaning that we're just recommending that this can be put into a register. You don't actually force the compiler to do that. The compiler will figure out if it can use a register as it compiles this code and converts this into machine code. It will look at the code and see if there's an available register. If it makes sense to do that, the compiler will go ahead and do it. Otherwise, it may not do it. So that's what's meant by its recommendation. It's just we're telling the compiler as a hint, you could put this in a register. If the compiler finds out it can be done, it will do it. Otherwise, it will just ignore this recommendation. make sure to understand that this is not always going to be in a register. It depends on what the compiler figures out as it compiles the code. Okay, so that covers register. That's it for this lecture. See you in the next lecture. Let's look at the third keyword, static. With static, we need to use another function to understand it more. Let's say we have a function called print number, and I wanted to print here, let's say integer n equals 0, print number equals, and we pass it n here. Now let's do something as the following. Let's say n++. Okay, so now we come here at the bottom and we say print number. Let me copy paste this 4 times. As you can see, now I have it 4 times. So now let's run this. Control F5 to compile and run. Yes. You can see at the very bottom here, number equals 111. This is a local variable, gets always allocated and deallocated with a function. We do n++, it's always going to be initialized to 0 and then incremented by 1. Here's where the static keyword inside a function is useful. If we say static integer n, that means you can treat n as a global variable, meaning that you can only initialize it once, define it once, initialize it once, and from that point on, it doesn't get initialized again and again. So it becomes like a global variable. However, from access scope perspective, it's considered a local. So let's go to the definition here so that it's probably more clear. Static can be defined within a function. If this is done, the variable is initialized at compilation time and returns its value between calls. Static is the default storage class for global variables. To make this more clear, static means that the first time you call the function, this gets allocated and defined, initialized only on the first call of the function. The next subsequent calls, it will not do it. It will just be treated as a global variable with local scope. So the next call in will not initialize. So this gets executed once on first call. And then subsequent calls, this will be ignored. So that means that it can return its value. So now the output should be different. So this means this first call will allocate and initialize n. This will not be executed on subsequent calls. So let's see this in action. This should automatically increment. And let's compile this, Control F5. Yes. Now, as you can see, the first time n got initialized to 0, and then we said plus plus became 1. Then subsequent calls became 2, 3, 4. Now n is behaving like a global by the introduction of the static keyword, and it can return its value. There's a lot of use for this as we progress through programming. As we learn more and more, you will realize that this is very useful in many ways. Let's now switch gears and talk about the keyword volatile. Volatile keyword specifies that the value associated with the variable can be modified by actions other than those in the nearby code. Volatile keyword is useful for declaring data in shared memory, so it can be accessed by multiple processes or by interrupt service routines used for communication and things of that nature. When you define a variable as a volatile, the compiler will always reload the value from memory. Even if the compiler looks at the code and thinks, oh, this value can be optimized away, it will not do that. Once it sees the word volatile, that means do not optimize it. This prevents the optimization compiler from making any changes to the variable. It doesn't try to optimize it away. It's mainly used to ensure predictable program behavior. Let's look at an example. Here's an example. So I have defined an integer volatile done as a global variable. And you can see that volatile usually is for global variables. So this means that you tell the compiler, hey, don't try to optimize this away. Don't try to see that, oh, 0 is not going to be changed. For example, let's assume this code was somewhere else. The compiler will look at this and say, hey, this value is always 0. Might as well just get rid of it and use a hard-coded value. Don't put it in memory and use some kind of a fixed constant variable. So that's why you say volatile, to prevent the optimizing compiler from actually removing this variable. And why is this needed? Because there's some other code somewhere else is going to change the value here. For example, here's an example where it's an interrupt routine. It looks at some transmission communication. It says, oh, the end of transmission has been received. At that case, it sets it to 1 so that we can exit out of this loop. That's why volatile is useful. But this is one of these keywords that are rarely used by majority of developers. In this lecture, we'll learn about a new keyword called typedef. C programming language provides this keyword so we can use it to give our types a new name. For example, if I say here unsigned char I, what I'm really saying here is that I want to use I as a byte that can take values from 0 to 255. Instead of doing this over and over again, I could simply come here and say type diff unsigned char to be byte. So how do you read this? Think of this as the following. The last keyword here becomes a new data type, which is an alias for whatever is in between this keyword and the type diff keyword. So everything in between, this becomes the new alias for it. So now I can say, instead of this, I can say byte I. The Visual Studio IDE is smart enough to highlight this for me so that I know it's a type. So this is very useful so that we can start defining, byte n, for example. We can say n equals I. So now we have a new type. This is also useful with things of like, let's say, other examples, type diff const char pointer. I could call this to be pointer to static char, for example. Just an example of how we could use this. So now I can say pchar p. So now p is a pointer to a static character. In fact, in the Windows.h, you will find that Microsoft has used this a lot. It could say something like type diff const char pointer bcstr, which stands for pointer to constant string. And they have defined so many things of this nature, like something like this pstr, pointer to string. So Microsoft is using this heavily in Windows.h, and this is another example of using it. Another really useful way to use it is with structures, because in C we have a struct like this, struct, for example, rectangle that has integer x1, y1, and then integer x2, y2. Now if we want to define a variable of this type, we always have to say in C struct rectangle rc1. This becomes tedious if you try to use it, like this multiple times. Instead, you can come here and say, I want to define a new type, type diff struct rectangle rect, for example. Now, I can come here and just substitute all of this with the word rect. They're exactly the same. It's just an alias, another type definition for the same type that we already have. So type diff gives you a way to add a new type definition to the vocabulary of the language if you want to consider it that way. So basically now I have rect. Let's say this was in a different file, or the file is too long. You don't know where this thing is defined. You can come to this, like for example, the byte. I don't know where it's defined. Just on the keyboard, when you have the cursor hovering over it, just hit F12. It takes you back to where it's defined. Another way to look at this to know where it's defined, you can right click and say go to definition, which is the same as F12. It will take you back to where it's defined. We should use meaningful type definition names so that we don't have to go back and figure out what it means. That's why when you look at it like this, for example, BSTR, you should quickly know that this is a pointer to string. You don't have to go back always to figure out where's type diffed. So this is pretty much how we use type diff. It's very useful to use and allows you to introduce new type definitions, aliases if you want to call it, to an existing type. And remember that the way you define it is that you put all the keywords that you want to type diff between the type diff keyword, and the final one is the new type diff keyword. So that's it for the type diff lecture. See you in the next lecture. External storage class in C and C++. What is the external storage class and how do we use the external keyword? Let's start with the definition. In C, an external variable is a variable defined outside any function block. External variables can be accessed by name by any function in any source file in the same project, also known as compilation units. External variables are globally accessible because the external keyword applies only to global variables. They return their values because they're globals. To declare any global variable as external, you simply add the external keyword. So in this example, we have an integer count. By using the external keyword, simply that means this count is not a new variable. It's an external variable defined in some other file. In your project, you can do this one or more times. you have like 10 files, you can do this in 10 different files, but one of them has to be declaring the global variable like this. It has to say integer count equals some value, but this must appear once in the project because this is the place where it gets declared, defined, and initialized. To make this more clear, let's look at an example. Okay, so in my example here, I have two files, file1.c and file2.c. Notice that on the left, file1.c is the main program file. In here, I declare an integer count equals 10. This is a global variable declaration. Inside main, I'm going to print out the count. Then I'm going to call a function called foo that's not in this file. And afterwards, I'm going to print out the count again. Now, we're going to declare foo in a separate file, file2.c in this example. Foo function simply sets the count to 20. But however, the compiler treats each of these two files as a separate compilation unit. If you try to compile this alone without the line at the top, then the compilation will fail because the compiler will say, I don't see count defined anywhere. It doesn't exist, so it will give you an error. That's why we say extern integer count. If you simply say integer count, in C compilers it assumes it's an extern if it was defined somewhere else. However, we need to explicitly say this is an external variable. That's why we use the extern keyword, because we want to make sure the compiler understands we're not declaring a new variable. We're saying this is an external global variable that we want to reference here. So by using the extern keyword, we tell the compiler to look for the global variable declaration and definition here. And it simply links this to this one. So it knows that this is the same variable as this. So what happens in this program, it will print out 10, calls foo. Foo will set this variable to 20. Next one will show 20 on the command line. So the result of our program here is going to be count equals 10, count equals 20. All right, so that's it for this lecture. In the next lecture, we will jump into Visual Studio and try this example ourselves. See you in the next lecture. Okay, so here I am in Visual Studio. Let's go ahead and create a new project. Click on File, New Project. Make sure you have Visual C++ Win32 from this list and then click on Win32 Console Application. Let's call it Extern Demo. Click OK. On this page, click Next. Click Empty Project because we want to create a C project, then hit Finish. To add main.c, we need to right-click on Source Files, Add New Item, and then let's call it main.c. After that, click Add. Okay, in this lecture, we will see how to use the extern keyword. Let's assume we have an integer count equals 10, which is a global. And now I simply want to print out that global. Count equals %d count. After that, I'm going to call a function called foo. And then I'm going to print out the count one more time after that. As you can see, in this file, there's no function called foo. So let's go ahead and create this function in a second file. So right-click on Source Files, Add New Item, and we can call it test.c or file2.c, or I'm going to call it foo.c. Click Add. As you can see now, in my project, I have main.c and foo.c. Double-click on foo.c. And let's implement the foo function, void foo. And what I want to do is I want to change the count to 20. However, as you can see here, the compiler is complaining. Already, it's telling me with a red squiggly that the count is undefined. This is because each file is considered a separate compilation unit. In fact, if you right-click on foo.c here and click on compile here or Ctrl F7, we're going to get a compilation error here. In the output window, as you can see, count is an undeclared identifier. So how do we fix this problem? How do we tell it that I want to refer to this global count in the main.c? And that's where we use the extern keyword. We say extern integer count. Not only this takes care of the compilation error, this also means that count is not a new global. It's actually an external variable defined in some other file in the project. Okay, now let's compile this project. Ctrl-Shift-B on the keyboard to compile. Compilation is successful. However, I'm getting a warning. Foo is undefined, assuming extern returning integer. What does that mean? in main.c, let's go back to main.c, double click on this warning. It'll show you that the compiler is warning us it doesn't know about foo. This is because each file is its own separate compilation unit. So to fix this problem, we should take this function prototype and place it inside the foo.h, a header file, then include that header file inside main.c. We should include foo.h here. Now, just because this is a small program with one function, we can actually manually do the forward declaration here. We can simply say void foo here, and this is exactly the same as creating a foo.h header file and then including it here. Instead of doing that, I'm just saving myself some time. I'm just gonna manually declare it here. So this is called forward declaration. So now let's compile again, Ctrl+Shift+B. Now you can see I'm successfully compiling here with no errors, no warnings. Cool, let's run this, Ctrl+F5. And as you can see, the output is count equals 10, count equals 20. And that's because initially count is 10. That's the first output. Then we call foo, which is in another file. And this foo operates on the same global because here we say it's an external integer count. What is the static storage class and how do we use the static keyword in C? Let's start with a definition. In C, static can be used with global variables as well as functions. When using static with global variables, that means the variable is not going to be visible outside the file it's defined in. Also, when you specify it on a function, it also means that the function is local to the file it was defined in. So let's jump to Visual Studio to see how we can actually use the static keyword with the global variables as well as functions, and also learn when we need that. Okay, so I'm in Visual Studio. Let's go ahead and create a new project. Click on File, New Project. Make sure you have C++ 132 selected, then click on Console Application. Let's call this one Static Demo. Click OK. On this page, I'm going to click Next. Make sure you select Empty Project here, then click Finish. We're going to need to create our main.c, so right-click on Source Files, Add, New Item, and call this main.c. Click Add. Okay, in this lecture, we want to learn how and when to use the static keyword in C. In previous lectures, we learned about how to use static keyword within a function, like if we have a function here, test. We have learned in the past how to say static integer count here equals 10, for example. In this case, count is considered like a global variable in terms of retaining its value and keeping its value, but at the same time, it has local function scope. So even if the function exits, every time you call the function, it will always increment the count. First time it will be initialized to 10, and every time you call it, it will be always incrementing the count and keeps the last value. So if you exit with 11, the next time is going to be 12, 13, etc. So this is not what we want to talk about today. We've discussed this in a previous lecture. Today we want to see how and when we can use the static keyword to limit the visibility of a variable in C into a single file. And let's start with this example. Integer count equals 10. I'm going to say here printf count equals %d and then pass it count here. Then I'm going to call a function called foo and also print the result afterwards. Now we're not going to declare foo in this file. We're going to add another file. So right click on source files, add new item, and let's call this one foo.c. Inside foo.c, I'm going to say void foo, then say count equals 20. Count is not defined here, so we have to define it. We're going to say integer count equals 0 initially. Okay, so now what's happening here is that inside foo.c we have a global called count. It's initialized to 0, and then later on foo will set that count to 20. We go to main, there's another global called count, initialized to 10. Main is trying to print it out, calling foo afterwards, and then printing out count again. So if we compile this, we're going to run into an issue. In fact, there's two issues here. The first one is that foo is not defined. The second one is that the linker is complaining that the count is already defined in main.obj and foo.obj. So that means two separate compilation units, foo.c and main.c, both have defined a count, and at link time, the linker sees both global variables. It cannot work with two global variables with the same name. So how do we solve this? In a previous lecture, we looked at extern. In that case, our intent was this variable to be the same as the one in main. However, there are scenarios where you just got some library from somebody else who happens to use the same global variable name as your code, or maybe two different libraries from two different people both have used similar variable names. So to avoid name collision like this, that's when we use the static keyword. If we simply go to foo and say static integer count equals 0, in this case, what we are saying here is that count is only visible inside this file. It's not going to be visible outside. By default, global variables are going to be visible outside the compilation unit. At link time, they will be visible. However, if we do this static here, it's not going to be exported outside this compilation unit. So if we compile this, Ctrl+Shift+P, we should get rid of the problem there. So now, as you can see, foo.c successfully compiled. There's no issues here. However, we still have one single issue, which is, let me rebuild solution. Oh, we still get this problem. Foo is undefined, assuming extern returning integer. This is because foo is not defined in this compilation unit. We should have a foo.h that declares this function, but instead I'm going to just copy this and put it here with a semicolon. This is called forward declaration. So now Ctrl+Shift+B to compile again. As you can see, we successfully compiled with no errors, no warnings. Let's run this and observe the output. As you can see here, now count is 10 and count is 10 again. What is happening here is that count has not changed here because foo now is no longer able to access that global inside main.c. It's actually operating on its own count here. In fact, let's print it out. Let's say printf foo count equals %d. And let me actually make this even more interesting. Get rid of this. And let's put here the value 1, 2, 3. Okay, so now what I'm doing, inside main, count is 10. It prints it out, calls foo, and then prints out count again. Foo.c says foo so that we know it's inside foo. Foo count equals, and it's referring to this global, which is static, which means that it's global to this file, but it's not visible outside this file. So let's run this and see the output. Oh, we have another issue here. Every single file is its own compilation unit, so we have to include standard IO here because we're using printf. Okay, so now let's compile again, Ctrl+Shift+B. My guess here is the output is going to be 10, then 1, 2, 3, then 10 again. Let's see it in action. Ctrl+F5. As you can see, count is 10, foo count is 123, and count again is 10. And that shows you the power of the word static. Static applies to global variables as well as function names. Let's see a case here where we have another problem with functions. Let's add a function called print hello, printf hello from foo. Okay, I'm gonna copy this function and then paste it into main.c. I'm gonna also put that in here. And now I'm gonna call this function here at the end, saying print hello. Let's compile this, Ctrl+Shift+B. As you can see now, we're getting a similar error here. It says the linker is complaining print hello already defined in foo.obj. So when it's trying to compile main.obj, it found out that foo.c already have print hello. Again, the problem here is that there's a symbol here defined more than once, which is the print hello symbol. I should actually make this hello from main. So we can either say static here for this one, or place the static keyword in the foo.c. Let's do it here first. Let's say static void print hello on the main. So now if we compile, Ctrl+Shift+P, you can see the error is gone, and we successfully built. So let's run this, Ctrl+F5. Now as you can see here, hello from main. What happens if we take this static out and then place it in foo.c? If we just say this is static here, what we mean when we say static, that means this function is only visible inside this compilation unit. So it doesn't matter if we do it on the main.c or foo.c. I just wanted to show you both cases. So now we have the static on foo.c. So let's compile this, Ctrl+Shift+B. Okay, successfully compiled. Let's run again, Ctrl F5. And as you can see, the output is the same, nothing has changed. You can either use the static keyword inside foo.c or main.c. The idea here is that we use the static keyword whenever we want to avoid name collision at link time. You just need to learn about static so that when you run into cases where you're not able to compile your code with some other external code, you can either have one of two options. You can either change the names in your own code if you think that's not a big change or it's a safe change, or you can simply use the static keyword to avoid the compilation errors. Alright, that's it for this lecture. See you in the next lecture.